Hi everyone. Today we'll take a look at modulus function, also known as the absolute value function. So the modulus function of a number is its distance from zero. So let's take a look at a few examples. All right. So let's change the color. Let's go to red. All right. So we have, for example, modulus of -2. So modulus of -2, or the absolute value of -2, is 2, right? And the absolute value of 2 is also 2. So what it means is we're asking what is the distance of -2 from 0? Well, it's actually 2 units just to the left, right? The direction doesn't matter, right? So let me draw a number line here. So let's make it a little bit more clear, right? So if I have a number line right here like this, right? These are my arrows, right? So I have maybe 0 here, 1, and 2, and I have -1 and -2, right? Something like this. So now if I want to find, so I know -2 is here, right? I know -2 is right here. So if I want to find the distance of -2 between -2 and 0, I can just count the number of steps, right? So 1, 2. So the distance to here, it's just 2 units, right? So I can say the absolute value, or the modulus of -2 is 2. Similarly, what is the distance between 0 and +2? Well, it's also 2, right? So it's also 2 units right here, this way, right? So this is also 2. So essentially, when we talk about, modulus is like the distance, right? It's the distance. So it's the distance, which is always positive, and distance is always positive. So you can always say that modulus of any integer, positive or negative, is always positive, right? So for example, let's consider that we have, some sort of a function at this point, right? We can assume a function, right? So maybe we have, 2 minus 2, negative square root of 2, and 0, right? These are our inputs, right? This is what we enter in a function, right? And think of function as a machine, right? So if I have a machine, right, and the machine is my function, right? So my function is modulus of x. So if I, insert all of them inside the function, right, they're going to spit out, certain value, right, corresponding to the input, right? So for 2, I'm going to get a 2 because the modulus of 2 is 2. Modulus of -2 is also 2. Modulus of negative square root of 2 is also square root of 2. Now just know that the negative sign is outside the square root. It's not inside the square root. So this is, it is a real number, right? So, and the square root, and sorry, not the square root, modulus of 0 is also 0, right? So these are the values that I get upon using the modulus function, right? So let's understand the modulus function, as graphically as possible, or what it actually means, right? So let me change the color again. I'll take yellow, right? So modulus function, right? Modulus function in simplest terms, right, is y is equal to modulus of x, right? Now we can break this apart, right? So basically modulus of x, or I'll do it here only. So modulus of x, like this, is equal to x and minus x, right? Now it's like a piecewise functions, if you remember this, right? If you know what this is, right? So if x is greater than or equal to 0, and if x is less than 0. So this is how you can break your modulus function into two piecewise functions, right? So now if you want to graph this, right? Well, before graphing, let's understand the domain and the range as well, right? So the domain here, it can accept any values. There is no restriction. This isn't a rational function where the denominator cannot be 0, right? Or it's not a radical function where everything inside the square root must be greater than or equal to 0, right? So there is no constraint in this function as far as the domain goes. So I can say that the domain, right? The domain is all real numbers, right? All all real numbers, right? That's not an issue either, right? Now the range is not all real numbers, because remember what I said about modulus. Modulus is always positive. So the smallest value that you can get is 0, right? 0 and all positive numbers. So our range basically is from 0 to infinity. Now again, all with infinity, we always use a parentheses or a curly bracket. A curly bracket is actually this, not this. So I'm going to say parentheses every time, right? But we can include 0, right? Because we just saw right here, the modulus of 0 is 0. So I'm going to put a square bracket right here. So it's inclusive of 0 to infinity, right? So now let's graph the function, right? So I'm gonna take white now, draw the axes like this. I'm gonna plot basically y is equal to modulus of x, right? So like this, right? So I can plot a table here if I want to as well. So I could get my x right here, and then I can get my y here like this. So for 0, I'm gonna get 0, right? For 1, I'm gonna get 1. For 2, I'm gonna get 2. For minus 1, modulus of minus 1 is 1, right? And for minus 2, it is also 2. So let's go ahead and plot these points, right? So if I plot these points, I'll take line, right? So maybe I'm gonna get like 1, 1. I can even 1 and 2, minus 1, minus 2, 1, 2. Right, so I'm gonna get 1, 1 right here, 2, 2, 2 right here, minus 1, 1 right here, and minus 2, 2 right here. So essentially, now if I plot this line, right? So if I plot this, I'm gonna get like a V, right? I'm gonna get something like a V. So like this and like this, all right? Something like this, right? So now if we look at this closely, right? If we look closely right here, this graph is y is equal to x, and this graph is y is equal to minus x. And they change at 0, right? The turning point, I guess, is 0 right here. Right? Don't think of this as a turning. If you've done calculus, it's not the same turning point as calculus, right? Because this function is not differentiable at x equal to 0 because it is not a smooth turning point. It's a it's a corner point. If you it's an abrupt changing point. So it's not an exact it's not your calculus turning point. I'm just using that word so you just understand what's happening here, right? So it's kind of, you see this turning point like right here, right? So now you can see that this graph follows two different functions. So y is equal to x from 0 to infinity, and y is equal to minus x from minus infinity to 0, right? You can I've denoted it right here, but this is the important part. This is how any modulus function will work, right? This is the key, right? If you're required to plot the graph, you're gonna have to understand where the turning points will exist. It's basically whenever anything inside the modulus is equal to 0, right? So we equate x is equal to 0. So x is equal to 0. That's pretty obvious. And then whenever it's x is greater than or equal to, so that thing we have positive version of the graph. If not, we have the negative version of the graph. So we can look at an example right here, right? So I've separated this part. It's called the opening modulus function. So let's take a look at this part right here. So we have y is equal to x modulus of x minus 1, right? So let's break this apart using the same concept that we learned before. So we know that f of x is equal to modulus of x minus 1, right? So let me draw this. Let me write it a little bit more neatly. So like this, right? So I'm gonna break this again into piecewise functions. Now, how am I gonna do that? Whatever's inside the modulus, I'm gonna take that first. I'm gonna write x minus 1, right, is equal to 0. Okay? So I'm gonna write x minus 1 is equal to 0, right? So this is the part. This is my turning point, right? So if I'm gonna solve this, I'm gonna get x is equal to 1. So at x is equal to 1, I'm gonna experience this pointy turning point right here. Okay, in this case it's gonna be x equal to 1, not x equal to 0, right? That is one thing I'm gonna have to know, right? So what happens is I'm gonna have one positive version of the graph, one negative version of the graph. So I'm gonna have x is equal to 1 and minus of x is equal to negative minus 1, like this. Now when is it going to be the cases? So it's going to be if x is equal, if my x minus 1, right, is going to be greater than or equal to 0. So essentially, I'm going to have whenever x is greater than 1. And here I'm going to have when x minus 1, right, is less than 0. So I'm going to have x is less than 1, right? So I can rewrite this again, a little bit more simply, a little bit more neatly, I guess. So I'm going to have x minus 1 when x is greater than 1. And I'm going to have x minus x plus 1 when x is less than 1. So greater than or equal to 1 and x is less than, right? So this is my final, final, uh, essentially simplification of this modulus function, right? Okay, so now if I have to plot this function, how is it going to look? Right? So that's again, that's an important part as well. So I'm going to have my axes right here. I'm gonna draw, I'm gonna draw a very rough sketch. I'm not even gonna, label the units like one. This is one. This is two. I'm gonna draw a very rough graph just so you guys have a conceptual idea of what's going on here, right? So I'm gonna take this. So I'm gonna take, maybe this as one, right? And then I'm just gonna draw, x minus one. So x minus one is something like this because it's suppose. So it's gonna start. The y-intercept is minus one, and it has a slope of one. So I'm gonna have something like this, right? Now I know that it's from greater than or whenever x is greater than or equal to 1, I'm going to have that function. So basically, this part, which is x is less than 1, I'm going to erase it because there's no need of me having it, right? So I'm going to change right here. I'm going to make it partial. So I can erase this part right here. So I can erase this part, right? So now that I've done it, that's good right there. So now the next function I'm supposed to make is minus x plus 1. Right? So minus x plus 1 is a slope of negative 1 with the intercept at 1. So somewhere around here. So I can, do like this, right? Like this. Something like this. Right? Again, this function would go on like down like this as well. But it's this function, I only have to draw it till x is equal to 1. So I've already drawn it there, right? So again, it's not exactly 100% accurate, I know. But you get the idea of what I'm trying to do here, right? So I have my y is equal to x minus 1 here, and I have my y is equal to minus x plus 1 here, right? So I have both of my different curves right here, right? So this is how you break apart, um, modulus functions into piecewise functions, so then we can plot them and then find the range of them if we have to, right? Because the domain is, there is no restriction to the domain essentially, right? Maybe there might be a restriction to the domain later on if, you use, absolute modulus functions and rational functions, something like that. But otherwise, for now, there is no restriction in the domain. You just have to be careful of the range because the range will vary. It won't always be from infinity, from 0 to positive infinity. It can be from a negative number to infinity, right? But it's always going to be increasing because that's what a modulus does, right? Okay, let's look at a few example questions now. All right, so in this question, we have two parts, part A and part B. So f of x in part A is modulus of 2x minus 1, and part B is modulus of 2x and then minus 1 on the outside, right? So let's change the color first. So we have maybe peach, right? So let's take a look at modulus of 2x minus 1, right? So f of x is equal to 2x minus 1, like this, right? So I'm going to break this again. I'm going to break this, right? I'm going to write 2x minus 1 and minus of 2x minus 1. So basically, I'm writing, so again, you can basically write this as, f of x and then is equal to f of x and negative of f of x, right? That's exactly what I've done here. Like I haven't done, some rocket science work here. It's quite simple that way, right? So I've done that. So now, when will this exist, right? For what values of x? So whenever we have 2x minus 1 is greater than or equal to 0. Similarly here, we'll have whenever 2x minus 1 is less than 0, right? So if I simplify this, my y or my f of x is equal to 2x minus 1. And then I'm going to have minus 2x plus 1, right? Whenever here in this case, when x is greater than or equal to half, and in this case, x is less than half. Okay, so this is my piecewise function after breaking the modulus function, right? So now I can just plot these two functions based on the the restricted domain, and I'm good to go, like, right? I have no issue with it. So if I go ahead and plot this function, I'll change the color to white, make the axes. I'm not, again, very rough sketch, nothing too fancy here, right? So something like this, like this, like this, like this. Now, one key important aspect to notice here, right? The entire function is inside the modulus, right? That means no matter what value of x I take, the output, right, the f of x or the y, will always be positive, or at lowest it will be 0. It will never be negative, right? So I know that because it's not going to be negative, everything's going to be positive. That's one way to check your answers every time. One easy way is always to take some random values. X is equal to 2, x is equal to minus 2, plot them on the point, and then so on and so forth. But that can often be pretty time consuming, especially if you're getting marks, if you're getting points or marks for these working, right? If you're getting graded for this working, then taking random values and making then plotting the function is not beneficial, right? So you have to understand the concept behind this as well. So we know that the turning point is that x is equal to half, right? So I'm going to take this as x is equal to half, and then I'm going to take yellow. So it's 2x minus 1. So whenever x is greater than half, so I'm going to have 2x minus 1. So 2x minus 1, I can expect something maybe like this, right? Kind of like this. And similarly, I can expect something like this, right? So minus 2x plus 1, yeah, sure, why not? Like this, right? Well, this is like my 1, right? On the y-axis. Right, okay, so let's look at the second part of it now. So we have modulus of 2x and then minus 1. So in this case, this is slightly different. It's not going to be the same as this, okay? So let's break this apart as well. So I'm going to go to the next page, and I'll change the color as well while we're at it. So I'll take mint, right? So now in this case, it's much different, right? So f of x is equal to modulus of 2x minus 1, right? So now what I have to do is I'm only going to break this apart, right? I'm not going to write 2x minus 1 and then minus of 2x minus 1. No. I'm only going to reverse change the sign of the part that is inside the modulus. So I'm only going to write minus 2x minus 1, right? That's what I'm going to have. That's what's going to change here, right? And again, what is going to be my turning point here? It's not going to be a half, because I'm not going to 2x minus 1 is equal to 0. No, I'm just going to focus on the modulus part. So I'm going to write 2x is equal to 0, x is equal to 0, right? So whenever x is greater than or equal to 0, I'm going to have this. When x is less than 0, I'm going to have the second function, right? Okay, so again, 2x is greater than or equal to 0, x is greater than or equal to 0. That's why I put this right there, right? That is the only reason for me doing that. Right? Otherwise, I have I've done everything fine, right? So now these are my two piecewise functions, right? It's slightly different. It's not the same, right? So now if I have to plot this, I'll take again white to draw the axes, right? So draw this, this, like this, right? So I have my x, I have my y, right? I'll take yellow again, right? So now I'm gonna have a function like maybe like something like this. So it's gonna be like this, and then it's gonna be like this, right? It's gonna be something like this, where this is my x is equal to 0, and then my two functions change from here, right? Again, they are symmetrical, right? They are symmetrical, agreed. They won't always be symmetrical. If you have multiple moduluses, inside, when you're adding multiple modulus functions together in a function, which we'll take a look at later, you won't always have a symmetrical curve, just a graph or a curve, if you want to call it, just to be aware. But again, this is how you break apart. You only focus on this modulus, right? This is the only thing that you play around with. So you have a positive and then a negative, right? And then you equate this to 0 also. So this is the key part that you have to remember. Otherwise, everything remains constant, right? Nothing else changes. Right. Let's take a look at a few more examples. All right. So in this question, we have to define f of x free of modulus and draw the graph. All right. So this is again a stepwise question, right? So the first thing that we do is we find the turning points, right? So how do we find the turn? There are two turning points in this case. So we might even have a function that goes like this, and then like this, or like that. You know, multiple turning points. So that happens when we have multiple moduluses or moduli. I'm not really sure which one. So when we have multiple modulus functions in the same function, right? So the two turning points here are when we equate x minus 1, modulus of x minus 1 equal to 0, and modulus of x minus 2 equal to 0, right? So we have x is equal to 1, right? X is equal to 1, and x is equal to, sorry, this is plus 2, right? So it's going to be minus 2, like this, right? So it's plus 2. Okay, so now how do we start, right? What I'm going to do is I'm going to draw a number line here again, right? Number lines are literally my best friends when I work with modulus, right? They keep things really clear, right? So you can never, falter when you work with this, right? And I'm going to draw a number line, so I'm going to have maybe like plus 1 here, and minus 2 here. Doesn't have to be to scale at all, right? So now I have that. So let's go back to purple. Okay, so now when I have values greater than x is equal to 1, right? When my values is greater than x is equal to 1, my f of x will basically be, because it's positive, I'm going to have x minus 1, right? And then so this will be x minus 1. And when it's greater than when my x is greater than 1, it's also greater than negative 2, right? So this will also be as it is, right? So it's going to be x plus 2, right? So what I'm going to do is I'm going to quickly change the color and write it in blue again, right? Like this. So, right, so I'm going to have x minus 1 plus x plus 2 because they're both greater than 1, right? So this one, I'm going to call this region A right here, right? So this is my region A, right? It's pretty simple. So if I simplify this now, my new function, my simplified function will be 2x plus 1. Let's look at this region. When my x is greater than negative 2 but less than 1. So when I have this region, right, I'm going to call this region B. So region B. In this region, my x minus 1, this is going to be negative. So it's going to be minus of x minus 1, right? Minus of x minus 1. But this is still acceptable because it's still greater than all of these values. So I'm going to have plus of x plus 2, right? So this is going to simplify down to minus x minus 1, right? So minus x plus 1 plus x plus 2. So minus x plus x will cancel. I'm going to have f of x is equal to 3. Okay, now this is my final region C. Okay, so in region C, both of them are negative. Both of the value x will be less than minus 2 and 1, right? So I'm going to have negative functions for both. So I'm going to have minus of x minus 1 plus, or I can say just minus of x plus 2, like this, right? Both of them are going to be negatives. So, or if I want to technically do a technical way of denoting this, it's more like saying plus negative of x plus 2. So something like like this, right? So this simplifies down to minus 2x minus 1. Okay, so these are my three functions. So function, these are the three piecewise functions when I remove the modulus from them. Okay, so now if I want to rewrite this in a neater way, I can change the color and I'll write f of x, okay, is equal to minus 2x minus 1. It's equal to 3, and it's equal to 2x plus 1. Right? It's all equal to all of them. So now it all depends. When x is less than 2, I have this. When x is less than or equal to, greater than or equal to 2 minus 2, but less than 1, I have this. And when x is greater than or equal to 1, I have this, right? So these are the three different functions I have when I remove my absolute value. right? Again, it is the same way as we did the previous question. It's just that we have two different modulus functions here, combined into one, right? They're being added or subtracted or whatever, right? So we just have to look at, wherever the turning points are, that's where my function will change, right? So it is at 1 and 2, right? So at 1, so from minus infinity to, sorry, minus 2 right here, minus infinity to minus 2, it was something, then from minus 2 to 1 it was something, and then from 1 to infinity it's another function altogether. So when, if I want to plot this function, I'll do it on the next page. So I want to plot this function, I'll do it right here. All right, if I want to plot this, it's going to be like this and like this, right? Again, one more thing to understand here is that this is inside a modulus and this is inside a modulus and it's being added, right? So this is positive, this is also positive, right? And two positives, when two positives add, they'll always give a positive number. So my f of x, the range of my f of x will always be positive. Now, it's not necessarily it'll be from 0 to infinity, right? Now that's what we're gonna find out right now, right? That's what we're gonna find out right now. Okay. So when I plot this function, right? So if I take a look at here, right? So from minus 2 to 1, it's just 3. It's a straight horizontal line at y is equal to 3. So maybe something like this, right? And then, so this is 3, okay? And then it's just like this, and then it's like this, right? Something like this. So this part of my function, right, is y is equal to 2x plus 1. This part is y is equal to minus 2x minus 1, and this part is y is equal to 3, right? So this is, at 1 comma, this is at 1 comma, this is when x is equal to 1, okay? So x equal to 1, or, I'll just write 1 here, right? This is when x is minus 2, so these are my two turning points right here. So I'll change the color as well. I'll use pink, right? So this is one turning point, this is another turning point, right? So right here, right? So this is what it is. Again, it's not too complicated. You just have to work on it step by step. Rewind and watch this entire question again, because all of the questions are going to be, from this, right? You're gonna have to use the same approach every single time, right? Again, you can always, put in multiple values from, minus 10 to 10, and then you'll get the same approximate graph, right? You can do that, but you're never going to get marks for that, right? Because the examiner wants to see how you broke it down and understood the entire question, right? They want to see that. They don't really care. Any child, even like a 15, not even a 15, sorry, 10-year-old can, find different values of y's for different values of x, and then plot the graph, right? But that's not the key understanding, key takeaway from this concept, right? All right, so let's look at, one more question, and then we'll, do something else. In this question, we have to define f of x free of modulus, right? So we have modulus of x squared minus 1, right? Again, I'm gonna, just do it, and I'm gonna talk, as simultaneously. I'm not gonna do it step by step, right? So we break this apart again into two parts, right? So we find x squared minus 1, we find its turning point. So x squared is equal to 1, x is equal to plus or minus 1, right? So plus or minus 1, right here. X is equal to, sorry, let me write it like this. X is equal to plus or minus 1, right? So these are my two turning points, right? So I'm going to have x squared minus 1 when or if x squared minus 1 is greater than 0. And I'm going to have x squared minus 1 if x squared minus of x squared minus 1, right? Negative of f of x when x squared minus 1 is less than 0, right? So when am I gonna have these two cases, right? So the key understanding, right? We're gonna use what we learned previously, if you remember the wavy curve method right here, right? So I know my turning points are plus and minus 1, but how it's gonna work out, I'm gonna have to use my inequality here. So right, if I have something like this, right, greater than or equal to 0, I'm gonna have x minus 1 and x plus 1, right? Remember, the first step was always to write in factored form, right? I'm not gonna solve as I did before. I'm going to make factors. If it's possible, I'm going to make it, right? X minus is greater than 0, equals 0, right? My critical points are -1 and 1. I'm going to draw a number line right here, right? I'm not doing this, slowly, because this is something I've explained in the previous video. You can check it out later. Okay, it's called the wavy curve method. So I'm going to have -1 here and 1 here, right? I need positive values. So if I take a look closely, anything in this range is positive and this range is positive, right? And it's negative here, right? So basically any values greater than or equal to 1 or less than or equal to -1 will satisfy this inequality, right? So again, so here I can rewrite this entire thing, or I'll just draw it like this. When x is greater than or equal to 1, or x is less than or equal to -1. And here it's whenever x is between these two, right? So between -1 and 1, right? So this is how I can break it down every time, right? So again, if I want to rewrite this neatly, I'll do it again, not an issue. So so f of x is equal to modulus of x squared minus 1, right? Like this. And I'm going to have x squared minus 1 and minus x squared plus 1, like this. Well, let me draw the semicolon a little better. Okay, so like this. And I'm going to have between -1 and 1, and like this, right? So, or x is less than or equal to -1. Now, I'm not going to plot this. I'm not going to plot this, okay? But what I can tell you the general shape of it, I want you to plot it on your own, right? I've given you the two piecewise functions with the restricted domain as well, right? It's going to come out something like this, right? I'm just going to draw, a very rough sketch of it. What you can do is you can plot it on your own on a piece of paper when you're free, and then go on Desmos and just plot this function on it, right? All you need to do is just plot this function, right? You don't even need to plot a piece in restricted domain. If you just plot this function, right, it will give you exactly what you're looking for. So what you're going to have is something like this, and like this. Right? It looks like a weird W, right? So, or if you want, I can change the color. So, see, so I'm going to have, it's going to be a parabola. So essentially this is x squared minus 1, right? But it's a modulus. So everything below 0 should be positive. So I'm actually going to have this, right? And what I'm going to do, make a dotted line right here. So dotted line right here, like this, right? So I'm going to drive a dotted line here, like this, right? So whatever is negative, it's just basically a mirror image with respect to the y-axis right here. Like that's all that's being done, okay? I want you to, you can try it on your own. Go to Desmos after you've, plotted the graph on a piece of paper, and then check it on Desmos, right? So these are the questions that we did so far. So now I want to discuss, something different, right? I don't know if if your teachers ever pointed this out in class, but I feel it's super important. Okay, so this is a very small concept. Right? I'm just gonna write it. It's like a note, right? Special note that you should keep in mind. Okay, I'm just gonna state it, right? I'm not even gonna explain it or anything. You can, it's real. When you see it, it's right there, right? So square root of x squared is modulus of x, right? It's not plus or minus x. Okay, it is not this, and I'll tell you why. We first do x squared, right? So whenever you square something, whether it's a positive number or a negative number, we get a positive answer, right? So because it's always, the inside is always positive, whenever we do a square, we're always going to get a positive answer, right? Because we can't have, technically you can't have anything inside it. You can't get a real value for a -3 or -4. But when you have -2 whole squared, right? So that's going to be 4, and the square root of 4 is 2. So technically you're getting a positive value every time. So it's working like a modulus function only, right? Or let me just keep it so you can use it for your reference, right? I'll just make this a little bit more neater. So it's 2, right? It's not plus or minus 2. It's just 2, right? So maybe if you have something like So you know what? Let me just directly give you guys an example question, right? So I'll change the color and we'll take blue, light blue. So if we have to, simplify, here, let me simplify the expression below, right? Simplify the expression. So simplify the expression for when a is less than minus 3. Okay. So this is already given to you, right? So and you're given the expression, let's say 9 minus 6a plus a squared, right? Plus 9 plus 6a plus a squared. So if you notice, these are perfect squares, right? So I can write this as 3 minus a whole squared and then the square root below it, right? And similarly, I can write the same similar thing here as well. 3 plus a whole squared below square inside the square root as well, right? Like this. So again, this is similar to the thing that I just explained right here, right? Something squared and there's a square root above it, right? So it's being squared first and then there's a square root on it. So this is basically 3 minus a plus 3 plus a, right? So it's exact. So basically, I'm having a mod. I can replace the squared and the square root with a modulus sign altogether. I'm gonna rewrite this, right? So I'm gonna write this as 3 minus a modulus plus 3 plus a. So now these are gonna have different values as well based on what a is, right? So here the question already says when a is less than minus 3, right? That's already been given here to us. So when a is less than minus 3, the critical points here are a is equal to 3 and a is equal to minus 3, right? So if I draw a number line here, again, same process being done here as well, right? I'm gonna have minus 3 here, I'm gonna have 3 here, okay? Now, so when you have something like this, right, this is okay. But let me tell you, you can also rewrite this as a minus 3, okay? Because I'm just, basically when I'm because it's the same thing, right? A minus 3 and 3 minus a is the same thing. Because it's like writing 3 modulus of 3 and modulus of negative 3. They're both equal to each other, right? That's exactly what I've done here, right? I've just changed the signs. I've made it negative, right? So I'm gonna write it as a minus 3 right here, right? And then I'm going to write this as a plus 3, which, commutative property of position allows me to do that. So a plus 3 right here. Now, again, this is, beyond minus 3 here, right? So once I've done this, then I'm going to check, right? It's beyond minus 3, all the way to negative infinity. So what I'm going to do is I'm going to write this as negative of a minus 3, and I'm going to write it as negative of a plus 3, right? And obviously it's being added with the negative sign, kind of overpowers the positive plus. So I'm gonna write it as minus a plus 3 minus a minus 3. So this gives me minus 2a, right? This is my final answer. So again, the whole point of this example question was to tell you how the square root of x squared is always modulus of x. And this is a question that you could come across, but I don't really think you will. It's possible, maybe not. So yeah, uh, this is all for today's video, and I'll see you in the next one. Bye bye.